The universe isn't just infinite. It's a masterclass in fractal complexity, where every pattern echoes the whole. Imagine a structure so vast and intricate that each part contains the blueprint of the entire cosmos. Today, we unravel the architecture of infinity itself, exploring how fractal forms shape the very fabric of reality and challenge our understanding of what's possible beyond boundaries. If you're fascinated by the infinite, the self-similar, and the mind-bending structures hidden in plain sight, you'll want to see how these patterns redefine the way we perceive space, time, and complexity. Foundations of infinity in mathematical thought. The concept of infinity has long challenged the limits of human understanding, especially within the realm of mathematics, where it transforms from an abstract idea into a tangible, even visual entity. At its core, the foundations of infinity in mathematical thought are rooted in the rigorous development of set theory, differential calculus, and the exploration of infinite processes. George Cantor's revolutionary work in the late 19th century introduced the idea that infinities are not monolithic but can vary in size, with some infinities being larger than others. His concept of different cardinalities, such as countable versus uncountable infinities, provided a formal structure that underpins modern mathematics' approach to infinity. This was a pivotal shift from earlier notions that treated infinity as a single, boundless concept, opening up new ways to analyze and compare infinite sets. In exploring the geometry of infinitude, fractal structures serve as an elegant bridge between the abstract and the visual. Fractals demonstrate how self-similarity persists at every scale, embodying an infinite complexity within finite bounds. The Mandelbrot set, for instance, exemplifies this beautifully. Zooming into its boundary reveals smaller, similar shapes anno domini infinitum. Such fractals showcase the notion that at every level of magnification, the structure continues endlessly, echoing the mathematical idea of infinite regress, but in a visually compelling form. These patterns are not just artistic. They embody the deep principles of recursion and self-similarity, which are central to understanding how structures can possess infinite detail without being infinite in physical size. Mathematics also approaches infinity through limits, a fundamental concept in calculus that describes how quantities grow closer and closer to an unbounded value, yet never quite reach it. For example, the sum of an infinite geometric series like 1 plus 1/2 plus 1/4 plus 1/8 approaches 2 as its limit. This notion enables mathematicians to make sense of processes that extend indefinitely, such as ongoing acceleration, wave propagation, or population growth, by assigning finite values to infinite sums or behaviors. It underscores a core principle, that infinity often manifests as an asymptote, a boundary approached but never crossed, embodying a foundational paradox that continues to influence mathematical and philosophical discourse. Complementing these ideas are the foundational questions about how infinity is represented symbolically and conceptually. The use of infinite symbols such as the lemniscate, infinity, or the idea of a completed infinity versus a potential infinity, as in an indefinitely continuing process, expands the scope of mathematical logic. This conceptual clarity allows mathematicians to craft theories where infinite sequences, series, and sets coexist harmoniously with finite mathematical structures. These foundations influence computer science, particularly in algorithms that deal with recursive functions and data structures, and underpin modern physics attempts to comprehend the universe's infinite extent. Thus, the architecture of infinity is built on a rich tapestry of ideas that continually evolve, challenging and broadening the horizons of mathematical thought at their most fundamental levels. The fractal nature of infinite structures. Patterns that repeat across multiple scales define the essence of fractals, and this recursive self-similarity underpins the concept of infinite structures in architecture. In nature, we see fractal principles exemplified in coastlines, mountain ranges, and branching trees. Each maintains recognizable forms regardless of zoom level. When considering man-made constructs, architects and designers harness these self-similar patterns to evoke the infinite, blending complexity with coherence. For instance, the intricate facades of certain modern buildings mimic the branching of vascular systems or snowflakes, illustrating how fractal geometry bridges organic forms and structural innovation. Mathematically, fractals are described by iterative processes that generate complex, detailed shapes from simple rules. These processes inherently produce structures that possess scale and variance. Zooming into a small part reveals a miniature, yet identical, version of the whole. This characteristic is crucial when designing structures meant to evoke the idea of infinity, as they can appear boundless regardless of how closely they are examined. The Mandelbrot set, for example, embodies this principle visually, but architects also translate fractal formulas into tangible forms, creating spaces that seem to extend indefinitely or possess an endless depth. In practical architectural applications, the fractal nature allows for efficient distribution of materials and innovative spatial configurations. Consider the example of the hierarchical fractal designs where larger structural elements are complemented by progressively smaller ones, creating a sense of harmony that echoes natural growth patterns. This approach isn't purely aesthetic. It also enhances structural resilience and adaptability. For instance, some avant-garde buildings incorporate fractal-inspired patterns in their ventilation or load-bearing systems, harnessing self-similarity to distribute forces evenly and optimize functionality across different scales. Furthermore, the concept of infinite structures through fractals extends into digital design and parametric architecture. Computer algorithms can produce endlessly complex forms by repeating simple rules, enabling architects to explore boundaries that traditional methods could restrict. These digital fractals often serve as visual metaphors for infinite expanses, such as endless corridors, recursive staircases, or layered transparency, that challenge our perception of space and limit. As a result, the architecture of infinity, rooted in fractal logic, opens a new horizon for experimental forms that seem to stretch beyond finite constraints, immersing us in spaces that evoke endless exploration and discovery. Visualizing infinity, patterns, and self-similarity. The concept of infinity in mathematics and nature often manifests through intricate patterns that repeat at various scales, exemplifying self-similarity. Fractals serve as ideal visual representations of this phenomenon, where each zoomed-in segment mirrors the overall structure, creating a seemingly endless tapestry of forms. These repeating motifs, like the Mandelbrot set or the Koch snowflake, challenge our perception of boundaries by illustrating that complexity can emerge from simple rules applied repeatedly. When visualized, fractal patterns evoke a sense of boundlessness, suggesting that the structure continues infinitely, even if our eyes, or tools, can only explore limited portions at a time. In practical terms, visualizing infinity involves appreciating how these self-similar patterns extend indefinitely, with each iteration revealing finer details without losing their coherence. For instance, the branching of a fern or snowflake exhibits a recursive buildup. Each small branch resembles the entire structure, and this self-similarity persists regardless of scale. Artists and scientists alike harness this property by employing recursive algorithms and computer-generated imagery to simulate natural fractals, revealing the infinite complexity embedded in seemingly simple forms. Such visualizations allow us to grasp the idea that infinite complexity often underpins the natural world, from the structure of galaxies to the microarchitecture of biological tissues. The interplay of patterns and self-similarity becomes even more striking when examining how fractals can be generated through iterative processes, repeating a rule or a set of rules over and over. When visualized, these iterative processes produce dazzling images that contain smaller versions of themselves nestled within larger structures. For example, the Sierpinski triangle, created by repeatedly removing equilateral triangles from a larger triangle, creates an infinite array of smaller, identical triangles that seem to extend endlessly in all directions. The visual experience of such fractals highlights how infinity can be represented through finite means, underscoring that the concept of endlessness isn't necessarily beyond our grasp, but can instead be encoded within recursive shapes and patterns. Ultimately, the beauty of visualizing infinity lies in the paradox that simple, finite rules can generate endlessly complex and self-similar forms. By examining fractal geometry, we see how the vastness of the infinite is embedded within practical frameworks, digital art, nature, mathematics, illuminating the notion that complexity and infinity are deeply interconnected. Whether through the infinite curl of a coastlines represented in fractal form or the repeating branches of a tree that seem to stretch into eternity, patterns and self-similarity act as bridges to understanding the infinite by making it tangible and almost comprehensible, one recursive layer at a time. Implications of infinite fractals in science and philosophy. The notion of infinite fractals fundamentally challenges traditional perspectives on scale, order, and complexity in both scientific inquiry and philosophical thought. Fractals, geometric shapes characterized by self-similarity across different levels of magnification, reveal that patterns repeat endlessly, offering a visual and mathematical embodiment of infinity within finite boundaries. This recursive structure suggests that the universe itself might be composed of nested, infinitely repeating patterns, blurring the lines between the finite and the infinite. When contemplating the universe through this lens, notions of chaos and order become intertwined, as fractal geometry demonstrates that complex systems can emerge from simple, repeated rules. In science, the implications are expansive. Fractals have been identified in natural phenomena ranging from the branching of trees and blood vessels to coastlines and mountain ranges. The fractal nature of these systems implies that their complexity cannot be fully comprehended through linear or Euclidean models alone. Instead, embracing fractal geometry enables scientists to better model and predict phenomena that display scale invariance, where similar patterns appear regardless of the zoom level. This has profound consequences in fields like physics, where the fabric of space-time itself appears to exhibit fractal properties at quantum scales, or in ecology, where population distributions and habitat structures follow fractal patterns that influence biodiversity and resource distribution. Philosophically, infinite fractals provoke reconsideration of notions like infinity, the universe, and consciousness. They suggest that infinite complexity can be embedded within simple rules, which echoes debates about the nature of the universe, whether it is finite but unbounded or truly infinite in scope. Moreover, the self-similar nature of fractals resonates with ideas about consciousness and identity, hinting at the possibility that individual selves or collective awareness might be composed of recursive, layered processes. This recursive architecture hints at a universe that is both patterned and endlessly self-similar, leading some thinkers to argue that understanding fractals could unlock insights into the fundamental nature of existence itself. The implications extend into mathematics as well, where fractal dimensions challenge traditional Euclidean concepts of dimensionality. Instead of being confined to whole number dimensions, fractals often possess non-integer dimensions, a concept crucial for describing irregular, fragmented, or highly complex systems. Scientific models incorporating fractal dimensions allow for more accurate representations of real-world phenomena, especially those that defy smooth, continuous structures. Philosophically, this introduces the idea that reality may not be fully describable through simple, linear measures, but through complex, layered constructs that embrace ambiguity and infinite detail. Ultimately, the study of infinite fractals blurs distinctions between the finite and infinite, order and chaos, suggesting that the universe's deepest truths may be embedded in endlessly repeating patterns woven into the fabric of existence. Usnovnoy, Rusgil 5. The architecture of infinity, viewed through the lens of fractal forms, reveals an intricate dance between complexity and self-similarity. This perspective emphasizes structures that echo their own patterns endlessly, echoing the infinite regression present in natural and mathematical systems alike. At its core, fractal architecture leverages recursive patterns, geometries that repeat at various scales, creating spaces that seem to expand without boundary. These shapes are not merely aesthetic. They embody principles of growth, resilience, and harmony found in nature, such as branching in trees or the rugged coastlines that seemingly stretch into eternity. Within this framework, the principle of self-similarity becomes a guiding force in design. For example, a facade inspired by fractal geometry might feature progressively smaller motifs that mirror larger elements, giving the illusion of infinite complexity. This technique can result in buildings that appear to morph when viewed from different angles or distances, making the structure seem alive and constantly evolving. Architects and artists keen on exploring the infinite often rely on algorithms and computer-generated models that simulate fractal behaviors, allowing for intricate forms that would be impossible to craft manually. The use of fractals invites viewers into a visual and spatial dialogue, one where the boundaries blur between the finite human-made and the limitless natural world. Diving deeper into examples, some contemporary designs utilize the recursive branching structures found in fractals to optimize both form and function. Gardens with fractal-inspired layouts, like the Fibonacci spiral, maximize space efficiency while creating organic beauty. In skyscraper design, fractal patterns can improve structural strength by distributing stress more evenly across multiple scales. The Eden Project in Cornwall uses geodesic domes that echo fractal geometries, combining sustainable engineering with captivating visual complexity. These examples highlight that fractal architecture isn't just about mimicking nature's aesthetics. It's about harnessing the mathematical principles underlying natural growth to craft resilient, dynamic, and visually captivating environments. The challenge and allure of constructing fractal-based spaces lies in balancing visual depth with practical considerations. While the repeating patterns evoke a sense of infinite continuity, every material choice, structural element, and functional component must also adhere to constraints of safety, cost, and usability. Advances in computational design tools have vastly expanded the possibilities, allowing architects to simulate and refine fractal structures with precision. As technology progresses, the potential for integrating fractals into urban planning and interior design increases, promising spaces that resonate with the natural world's endless complexity. This ongoing exploration hints at a future where our built environment reflects not just human creativity, but the boundless, fractal intricacies of the universe itself. As we've explored, the architecture of infinity reveals itself through the mesmerizing patterns of fractals, structures that repeat endlessly and embody boundless complexity within finite forms. From the recursive beauty of natural phenomena to the mathematical elegance underlying our universe, these patterns challenge our understanding of space and infinity. It's a reminder that the infinite isn't just an abstract concept, but something woven into the fabric of reality, visible in every layer of existence. If this glimpse into the fractal nature of infinity sparked your curiosity, stay tuned. There's so much more to uncover. We'll delve deeper into the science, philosophy, and artistry behind these endlessly fascinating structures in upcoming videos. Make sure to subscribe or follow so you don't miss out on the journey into the endless horizon of knowledge and wonder. Thanks for watching, and keep questioning the infinite. It's right there, waiting to be discovered.